Hello guys, so from today we are going to start a totally new series on reinforcement learning. The lecture notes I am taking have from are from Michael Painter and Skill. These are from Stanford University. This is CS 234, which is Stanford Stanford's reinforcement learning course. This is it. Okay, so what we know till now that the field of machine learning is divided into three subdomains, right? There is supervised learning, then there is unsupervised learning, and then the third one is reinforcement learning. Great. So what happens in supervised learning? I will say this: follow a guided form of learning. So what I mean by this term guided is that I am given with the data and I am given with corresponding labels, right? So my model, I will try to predict something from the data, and then I will match it with the label. I will match it with the corresponding label, and if that prediction is wrong, if it doesn't match, then I will go back. I will go back and I will retrain the model until this model fits fine. Right. So this label is actually a teacher or a supervisor which I am using to train my model on the data. Right. So this is supervised learning. Whereas in unsupervised learning, what happens is unguided. This is unguided form of learning. Now, what do I mean by that? See, I am given with data, but I'm not given with the corresponding labels. So this time I do not have the labels. So I have to figure out the pattern or the trend in the data without knowing the labels. So I do not have an external supervisor here. Like if you remember, we have clustering in unsupervised learning, right? We are given with certain data points like that, and we try to figure out clusters among them. Great. So this is unsupervised form of learning. Now third one is reinforcement learning. What happens in reinforcement learning? It is different from both of these, okay? It lies somewhere between supervised and unsupervised learning. So in here we have an agent. It takes some action on environment, okay, and it the environment gives it a feedback or it gets a feedback, okay, not basically from the environment, but it gets an feedback based on the action it takes. Now this feedback is in the form of reward. The general terminology that we use for that is reward, and now this reward can be either positive or negative. Now agent have this greedy thing that he wants to maximize the reward, so it will try to collect more of these positive rewards and less of these negative rewards. So it do not have any prior knowledge in starting. Then it tries with hidden trials, it gets reward, then it learns, okay, this thing is getting me positive reward, so I should do this more, and this is getting me negative rewards, so I should not do this, right? So this is what happens in reinforcement learning. Okay, so next thing that we should talk about is, okay, I told you, right, what happens in reinforcement learning, we are dealing with making decisions. We are dealing with making decisions and comparing actions that could be taken rather than making predictions. So it lies somewhere between the supervised learning and unsupervised learning. So let me read out this for you. Reinforcement learning lies somewhere between supervised learning, which gives strong feedback with label data. See, in supervised learning we have this label data, right? Label data, we do not have it here, but we do not have entirely no knowledge because we are have learning from rewards, right? So it is not entirely unsupervised and it is not supervised, so it lies somewhere in between of the both. So next thing what comes in this reinforcement learning is the trade-off between exploration and exploitation. So what do I mean by that? Okay, let me take a very basic example. See, suppose we have a city like this, and I want to reach from this place to this place. Okay, I know there is one route like this and there is one route like this. I know this one is a shorter route. Okay, this is inside my knowledge. Okay, so I exploited that knowledge so that I minimize the distance I have to travel to reach this point. Okay, I need to reach from A point to B point, and I know this is a shorter route, but I never went from another route. Suppose, let's say, there was a route like this. Okay, and it is more shorter than this route. It is more shorter than this route. Okay, but I never knew about that. So what I will do this time, I will try to figure out going from this route, or there are other routes which are maybe longer or maybe shorter. So if I always use this exploration, so from A, I'm exploring multiple routes to B. Like there is a route like this going from unnecessary places. It is going to cost me a lot of things. Okay, and if I am only always using the knowledge which I already have, like I knew that only I knew about this route only, right, in starting, that this one is the shorter route. So I will never get to figure out the route which was more shorter. I mean this route. I never get to figure out about this route. So there should be a natural trade-off between exploration and exploitation. So what we basically do is we use a, a small probability epsilon, and based on that we try to the come up with different techniques to maintain this trade-off between exploration and exploitation. We will learn about that later, but we should know that this epsilon probability is used for that. Okay, then there is this sequential decision making. Okay, what do I mean by that? So we have, let's say, AT means sequences of action, then OT means sequences of observations, and RT means sequences of reward. So what will happen? We have world, like this world, this is environment actually. Now what is environment? Environment is anything on where agent can take action, sorry. Okay, agent can take action on the environment, and then we have an agent. This may be a biological entity, or it may be a physical, non-physical, any sort of entity which is able to take action on the environment. So this agent takes an action on the environment, and according to that it gets a feedback. Now this feedback is observation as well as reward. Okay, see, see, reinforcement learning is based on the learning of human. Okay, a human child, when it comes into the world, it doesn't know that what to do. We just go out and try to do multiple things. Like when you were born, you wouldn't have knowledge that fire makes your hand burn. Okay, so someday in your life you would have just put your hand in fire, and you figure out that now this fire is the environment, right? You took an action, you put your hand in fire. Now what we get in observation and reward, we got a negative reward, right? Our hand burned, it felt pain, right? And observation, we figure out that fire generates heat. So this is what happens in reinforcement learning as well, but this time we are trying to train an agent which is basically, it can be a robot. Okay, let's stick with the terminology of robot in form of agent. So this is our agent. Okay, it have an antenna, and this is like that. Okay, so agent takes an action on world, which is environment, and then it gets back an observation and reward, right? So this process continues. That's why it is called sequential decision making, because we just continue this loop. Now we have algorithms like A star search algorithm and minimax search algorithm, which are used to just figure out things. See what happens in minimax. We try to minimize this, maximize the utility of. It depends on the perspective. Okay, it is sort of game playing algorithms. Minimax is among the game playing algorithm. A star search is a heuristic search. Okay, now modeling the world. What do I mean by that? Is can I make a simulation of the environment? So by modeling the world, I mean this simulation of the environment. So we are our agent. We cannot just make our agent learn on real world things. Suppose I have to make a car which drives autonomously. Okay, I cannot just put the car in the real world and see if it actually hits people or not. Okay, I need to work that before on some simulation. Otherwise, my car will be just go on a road rage. Okay, I do not want that. So modeling of the world is very necessary. So what we are given is as S be a set of possible states. See, state is something where or an instance of time, right? So what happens is like I'm given this with this, right? This is probability of state at time t plus 1. State at time t plus 1. Now time is something relative. Okay. So instance of time t plus 1 given. I'm given with, see, this is conditional probability. So state at time t plus 1 with given state at time t, action at time t, and so on to state at 1 time 1. Okay, this is t1, we can say that. And then action 1. So from starting, it is all the history of the agent. Okay, from the earlier state, we can figure out the probability of state t plus 1 given state t and at. So we use this Markov property. So what Markov property says is the future is dependent on the present irrespective of the past. Okay, now what do I mean by that? See, suppose I am here. Okay, this is my terrace. I am here. Earlier I was here, and maybe in future I fell from the terrace. Okay, so my future, this is my future. This depends on my present state, right? Rather than my past state. So see, if I know that I am on the edge of the terrace, I do not need to know that where I was in past, like I was at door or nothing. I will just say he was at the terrace at the edge and he fell off, right? To make this prediction, I only need to require this. Okay, so this is what I mean by that. And then we have components of reinforcement learning. Okay, we have an agent state, the present condition of the agent. Then there is a policy function. What is policy of function? It is mapping from agent state to an action. Okay, see, we have an agent state. Like I took this example, right? I was at the end of terrace. Okay, and earlier I was near this door, and in future I fell off from the terrace. Okay, now this is a probability, right? Because I do not know if I will fall from here or not, but this is a state, a possible state, right? So this is my agent state. If I am the agent, okay, I am taking myself as an agent. If I say this is a robot, then that is a robotic agent. Great. And this policy is represented with the symbol pi. Now what do this value function means? See, value function is the expected sum of discounted rewards. Now what do I mean by discount? See, discount factor is the same thing that we all learned earlier in the Markov property, is that the present, if we know the present, we can figure out the future is dependent on the present irrespective of the past. So my presence here will affect very less to future than my sorry, my past here will affect very less to my future state uh, instead of this present state, right? So this is what I mean by that. So this discount factor gamma is used for that. So what this means, that value of value function value for policy pi. Okay, value for policy pi at any state s is expected sum of reward, like this rt. Okay, let's take this example. I walk from here. Okay, this is me walking, and see, this is, let's say this is rt plus 2, this is rt plus 1, this is rt, and this is the next state. Okay, so what this is saying, see, I am taking rt as it is, then this gamma rt plus 1. Okay, I am minimizing it, like suppose say my discount factor is 0.91, so I will say 0.91 into r t plus 1. Great, so it is affecting less. Similarly, this 0.91 rt plus 2. Now see, this time I minimize it more, so I did 0.91 square. Great. And for state equal to s, so for my future state I am doing this. Okay. Now, taxonomy of reinforcement learning agents. So, what do I mean by that? Is we have some sort of agents. Okay, I forgot to tell you. See, there are two things. One of them is partially observable and fully observable. What do I mean by that? Is fully observable. Suppose we have a game of chess. Okay, everything will be observable within the chess because these 8 into 8 grid is all the set of all the possible moves will right here will reside here. Okay, all the possible set of moves will reside in this 8 by 8 cross matrix of the chessboard. So I am able to observe everything, and I am able to observe everything about the environment, right? So this is the fully observable environment. Whereas in partially observable environment, let's say autonomous driving, right? Auto driving car. So we do not know what will happen next. We cannot observe that. We only have knowledge about the things that we can see from the camera sensors of the car. Okay. Besides that, we will not be able to observe anything in the real world. So that will be a partially observable environment. So what happens in taxonomy of reinforcement learning agent? Basically, we have various type of agents. First of all, there is a value-based agent. In that, we'll have an implicit policy. So this mapping from agent to action, sorry, state to action will be implicit. Then we have this value function and model. See, model we can have or we may not have. Okay, in policy based we will have the policy. Okay, value function is not required, and then we can have the model or not. Then action critic agents, critic agents are like they will have a fixed policy, they will have a fixed value, and the model is again required or not based on your choice. Okay, and then there are model based agent which will require a full simulation of the model or the environment. So they will not require a policy or a value necessarily, but they will require a model. Okay, because they are totally model based. Then there is model free agent. Of course they do not require a model, so we do not want model. Value and policy, they are they may be required or not. Okay, so that's it for this video. Thank you.